Hey guys, welcome back. In this section 11.3, we're going to look at how atoms absorb and emit energy. How atoms absorb and emit light. So our first slide has a lot of stuff going on in it, right? You'll notice here's the nucleus of the atom. And then we've got these rings, these concentric circles going around the nucleus, centered on the nucleus. And what they're supposed to represent are the different energy levels for the electrons. Let's think about this. This is kind of a new idea. We're going to dig into this a little more deeply in the next section, but the idea is that an electron can be on this ring. This represents a certain amount of energy. It can't have less energy than that. These white regions are not allowed to electrons, so to speak, and these white regions in between the rings are not allowed to electrons. And so electrons can be on the first ring, on the second ring, on the third ring, but they can never be anywhere in between. You can almost think of this as ripples. Imagine that you dropped a rock into a glass smooth lake or pond. You would have a crest of a wave here, a crest of a wave here, a crest of a wave here. That's very much the way that physicists and chemists think about these things. All right, well, what's going on in the picture? Well, let's start up at the top. You can see this squiggly line represents an incoming photon that is absorbed by the atom. It can be a little more specific than that. The incoming photon, what's a photon? A photon is a piece of light. We're sort of mixing two separate ideas here. 300 years ago, there were two gentlemen, one named Christian Huygens, one named Isaac Newton, who had a debate about whether light waves behave like waves, right? And that's what you're seeing right here, the crest and the trough, the crest and the trough. So like a wave, or if light behaves like a particle. You're getting both of those things. It turns out they're both right. Today we think about light as a piece of something, in which case we call it a photon. So a photon just means a piece of light. We also think about light as a wave. They both work, sometimes better or worse depending on the circumstances. So the word photon means light. So incoming light, this orange squiggly line, is absorbed by the atom. I'm going to change this. I don't really care for this word. Technically, the incoming photon is absorbed by the electron. The nucleus, for example, has nothing to do with any of this. So the electron absorbs the light. Now this light is carrying energy. Light carries energy. As soon as the electron absorbs that light, it absorbs the light's energy. That means it can't be on this ring anymore. It has to jump up to a higher ring. This ring, this third ring, is higher energy than the second ring, which is in turn higher energy than the first ring. One of the analogies we'll use in the next section is it's kind of like a ladder. If you stand on the bottom rung, you've got the least amount of energy. If you stand one rung higher, you've got a little more energy. If you stand one rung higher, you've got a little more energy, right? So the electron absorbs the energy of the incoming light. As a result of having this extra energy, it has to move up to a higher energy level, a higher ring. Now, if you're really paying close attention, you say, Cato, I don't know if I buy this because you just told us that the electron can be on one of these circles, but it can never be in between, in this white space. And here's an arrow showing it moving through the white space. That's a misleading part of this picture. It turns out that in the same instant that this electron absorbs the light, absorbs the photon, it stops being on the first ring, and it appears on the third ring without ever passing in between. Now, if you're human and you're thinking about that, you're probably not very convinced by that. Here's an analogy. It would be as if you were in S108 taking chemistry, and let's just say that your next class after chemistry was biology. So you had to move from S108 across the hall into Mr. Damero's room. An analogy for this would be that the instant the bell rang, you would stop being in S108 and you would instantly appear in Mr. Damero's room without ever passing through the hallway in between. And you say that's clearly nonsense. That is probably the first claim that we're going to make in this chapter about quantum mechanics that is conceptually difficult. It seems like nonsense, and yet At this point, we're coming on 100 years of experiments demonstrate that that's exactly what happens. It's almost like a form of teleportation. So the electron stops being on this ring, appears instantly on this ring without ever passing in between. So that arrow is a little bit misleading, but you know, if you don't like the idea of instantaneous teleportation, sweep it under the rug, pretend it's not there. That's another time-honored scientific tradition, is to just ignore things you don't like. And you can pretend that the electron is moving through the intervening space if it makes you feel better. It won't have any effect on your success, your academic success in this chapter. So absorbing photons, absorbing energy, forces electrons to move up to higher rings, right? That's the absorb part. Now, before we move on to the emit part, there are different kinds of photons. There are different frequencies and wavelengths and energies of light. What's happening down here is we're showing an electron that is not on the first ring, like this one was. This electron is now in the second ring. It's absorbing a longer wavelength of light. Longer wavelength means less energy. This photon has more energy. More energy means a bigger jump. This photon has less energy because of its longer wavelength. That results in a smaller jump. So now we have an interesting scenario where how far the electron teleports, so to speak, depends on the amount of energy or the color of light it's absorbing. Bam! Depends on the color of light it's absorbing. Now here's an interesting question. Again, if you're being very human about this, you might say, well, what if it's not this much? What if it's a little less energy? But what if it's not this much either? What if it's a little more? What if it's in between these two? What happens? Oh, that's a beautiful question. And the answer is the electron can't absorb that light. Electrons only absorb light that gives them exactly enough energy to move from one ring to another. Let me repeat that. Electrons absorb only the amount of light that gives them precisely the amount of energy they need to jump from one ring to another. Any other color or energy of light, and the electron just lets it pass right through. Yeah. You say, really? Does that happen? Yeah, sure. Glass lets light pass through, doesn't it? It doesn't absorb anything, right? We'll beat that horse in a little more detail later. So there's the absorption. Here's emission. And if you look at the picture for a moment, you say, Cato, all you did was turn all the arrows around. Well, yeah, that's it, isn't it? Look, if this electron can absorb this exact color of light to go from the first to the third ring, then if it's going to go from the third ring to the first ring, instead of absorbing that light, it has to emit that exact amount of light. Same thing down here, right? Same thing down there. And so emission and absorption are the exact same process. They're just backwards or opposite of each other. Electrons absorbing light move up to larger rings. If you want to be technical, they're higher energy levels. Electrons that are emitting light are dropping down to lower energy levels. Finally, a little more vocabulary, a couple of technical terms. This smallest concentric ring is called the ground state. It represents the least amount of energy an electron is allowed to have in an atom. There's nowhere for an electron in a ground state to fall to. It turns out they can't fall into the nucleus. The why of that is a little bit beyond what we do, but the electron in the ground state can't fall any further. In other words, an electron in the ground state will never emit light. It can only absorb. All the rings after the first one are called excited states. These represent electrons that have extra energy. An electron in an excited state can always emit energy, emit light, to fall down to a lower energy level. And in fact, all of the electrons in an atom ideally are trying to get into the ground state. Now, sometimes they can't. Just like you and I are trying to get to the center of the earth, but because things get in our way, like the ground, we can't. Yeah. But that's where electrons want to be. They're going to get as close to the ground state as they can. Well, here's one more picture, and what this is showing, now we're using this ladder analogy. Instead of using concentric rings, we're going to say this ring would be this smallest ring would be the first rung on the ladder right here. Yeah, and then this would be the next ring, this would be the next ring, and so on and so forth. First thing you'll notice, of course, is that this isn't a very good ladder. The first rung is the tallest, and then each rung after that gets a little bit shorter. And if we kept on going, they get closer and closer together until they're all right on top of each other. We don't build ladders that way, but we still call it the ladder analogy. Next thing, energy absorbed is always bumping electrons up to higher energy levels. This picture is slightly misleading because it's incomplete. If you had an electron on 3, it could bump up to 4. It could bump up to 5. It could bump up to 6. It could bump up as far as 10,348 if it wanted, right? And you might ask a question, can I bump an electron to the infinitieth excited state? And the answer is yes, you can, and we'll talk about what that is later on. It turns out you've actually known that for months now, you just didn't call it that. And so adding energy can bump electrons up to any energy level, even though this arrow only represents one of those possibilities. All right, falling down. This is also slightly misleading because all of these arrows are falling down to the ground state, but there's no reason you couldn't fall from 6 to 5, or from 6 to 4, or from 6 to 3, or from 5 to 4, from 5 to 3, or from... You can fall from a higher energy state to any of the lower energy states. But ideally, electrons would like to fall into the lowest energy level that's available to them. Finally, what do we take away here? Well, falling from 6 all the way to 2, this represents losing the largest amount of energy. Purple is the wavelength of light that has the most energy. So an electron that falls from 6 to 2 is going to emit purple light. Falling from 5 to 2 releases slightly less energy. It's not such a big fall. So blue has a little bit less energy than purple. Falling from 4 to 3, okay, that represents even less energy. Green has slightly less energy than blue. And finally, falling from 3 to 2 is the shortest fall there is. That represents the least amount of light, and that's going to, the least energetic light, and that's going to be red. Couple of comments. First of all, these are all colors in the visible spectrum. There's absolutely no rule in the universe saying that an electron transition can't fall outside the visible range of light. It might be heat, it might be UV, it could be X-ray. Second, this is a gold arrow, and I'm not sure why. They really should have made this a purple arrow. If going from 6 to 2 emits purple light, then going from 2 to 6 ought to absorb purple light. I'm not sure why the author of this figure made that gold, but it really ought to be purple. Finally, you do not need to know the lengths of different colors of light. The N stands for nano, meaning billionths. The M stands for meter. This is 656 billionths of a meter. In other words, take a meter stick, chop it up into a billion equal pieces, and red light would stretch over 656 of those pieces. What you should take away from this is that the longer wavelengths have less energy, the shorter wavelengths have more energy. This is one you might have a lot of questions on. This idea is probably brand new. I'd be very interested to know if you've studied this before, but if you haven't, ask as many questions as you can, because if you're wondering, there's probably 15 other people in the class wondering too. Good luck.